In this lesson, we'll be discussing the process of how a Carnot cycle works, and we'll use a pressure versus volume diagram to demonstrate it. The Carnot cycle is named for Nicolas Léonard Sadi Carnot. He lived from 1796 to 1832 and was a French military engineer. Didn't live too long, died of cholera pretty young, but he is known as the father of thermodynamics. He developed the most efficient heat engine and laid a lot of the groundwork for Lord Kelvin and Rudolf Clausius's work on entropy. So, what was the Carnot cycle? It's a hypothetical reversible cycle that produces the best possible performance of a cycle. All the processes in a Carnot cycle are reversible, and it's got two reversible isothermal processes and two reversible adiabatic. So, to explain what it looks like a little better, we're going to have this diagram. On the left we have the process, which will go through each of the steps of the Carnot cycle, and on the right we'll show what's going on in the pressure versus volume diagram. So we have our first state. We're going to look at a piston in a closed system. So it's going to start out at a high pressure over here, low volume, so it's very compressed. And we're going to say that the temperature is at its highest temperature. And it's going to be sitting in a bath with the surrounding temperatures at the same temperature. So the thermal reservoir around it is the same temperature. So then when we go from state 1 to 2, what we're going to do is go through a reversible isothermal expansion. So isothermal, so the temperature is constant. So the temperatures are already the same, so you might be thinking, well, how does heat transfer going to occur if we hold the temperature the same? Well, in order to do that, we have to have another form of energy transfer, and that's going to be the work that's going to be leaving the system. So we're going to expand the piston, and that's going to cause, it would cause the energy to decrease, but since we have that heat transfer coming in, it balances it out. Okay. And so we see that we get to state 2, where we have a lower pressure, but a greater volume. Still at the same temperature, because I went through isothermal expansion. And now I'm going to expand it some further, but I'm going to take all the insulate, I'm going to insulate it now, and make it an adiabatic expansion. So now, I can't have any heat transfer coming in or going out. I'm going to expand it, so energy is going to come out due to the work. In order for the energy to go out, that would mean the internal energy of my system is going to have to decrease. If my internal energy is going to decrease, then if we assume this ideal gas, then that's going to mean that your temperature is going to decrease as well. So we're going to do this until we get to a certain temperature. We'll call this the low temperature. And it's going to be the same, it's going to be at state 3 here on the right. We're going to have it to be the same as another temperature bath, as our low thermal reservoir. So from state 3, we now have our piston completely expanded. We're at a low temperature. And now we're going to start compressing it again. So going from state 3 to 4, we're going to go through isothermal compression. So we're going to hold that temperature constant. We're going to have heat be leaving it, though. So in order to keep the temperature constant, as I compress, I am adding energy into the system by that work. In order to balance it out, I have to have heat transfer leaving out. So I'm going to have that heat transfer leaving. And you're going to see our pressure is going to increase as our volume decreases, until we get to state 4. Now at state 4, because I was isothermal, my temperature is still low. But now we're going to put an insulator around it. That's what this brown is supposed to indicate, is our insulation. And we're going to compress it some more. So now we're going to go through adiabatic compression. So now none of the heat transfer is allowed to go through the system. So now when I compress it, I'm going to increase the internal energy, which is going to mean that the temperature will have to increase. So I keep doing that until I get back to my initial state, where the internal temperature of the system is the same as the hot thermal reservoir. So that there is a Carnot cycle, a hypothetical reversible system. It's the ideal system for both the power system, as well as it can be used to describe the heat pump and the refrigeration cycle.